Every bridge you drive over is built to come apart. You felt it, that thump, thump, thump under your tires on a long bridge. Most people think it's just a rough patch in the road. Those gaps are doing something way more important. They're the only reason the bridge hasn't torn itself apart. Every gap is an engineered weakness put there on purpose. Without them, the whole structure would destroy itself in under a year. Here's the problem. Steel, concrete, asphalt, aluminum, all of it expands when it's hot and shrinks when it's cold. You can't see that in your kitchen, but stretch something across 1,000 feet of open air and the movement gets violent. Think about steel. For every degree Celsius the temperature rises, a steel beam grows by about 12 millionths of its length. Sounds tiny. But scale that up to a bridge spanning hundreds of meters and you get movement you can measure with your hands. Take a bridge with a 500-meter steel deck. In a lot of climates, the temperature swings 40 degrees between a winter morning and a summer afternoon. That deck grows by about 24 centimeters, nearly a foot of extra bridge appearing out of nowhere with nowhere to go. If the bridge were one solid, rigid piece, that expanding steel would push outward against its own supports with thousands of tons of force. And it works in reverse. Winter drops the temperature, the bridge shrinks, the steel pulls inward. Concrete cracks, bolts shear. The structure rips itself apart from the inside. This isn't theoretical. Engineers learned it the hard way. In the early days of iron and steel bridge building, before expansion joints were standard, structures cracked and buckled for reasons that baffled their designers. Bridges split in winter, supports shattered in summer. The cause was always the same. The bridge was fighting itself. The solution sounds too simple. You cut the bridge into segments. Between each segment, you leave a gap. When the bridge heats up and the steel tries to grow, the gaps shrink. When it cools and contracts, the gaps widen. The bridge breathes. But here's where it gets complicated. A gap in a road surface that cars are driving over at 70 miles per hour is a serious engineering problem. The gap has to be wide enough to absorb thermal movement, but narrow enough that tires don't notice it. It has to survive millions of load cycles. And it has to keep water out. The simplest fix is a compression seal, basically a rubber gland squeezed into the gap. Bridge expands, rubber compresses. Bridge contracts, rubber stretches. It's cheap, it works, and it handles gaps up to about 5 centimeters. Most short bridges you drive over use exactly this system. But for longer bridges, 5 centimeters isn't enough. The Golden Gate, the Millau Viaduct, the Akashi Kaikyo Bridge. These structures move so much that a single gap would need to be way wider. You can't put a 20-centimeter hole in a highway. So engineers came up with something called a finger joint. Picture two combs facing each other with their teeth interlocking. The deck on one side has steel fingers that reach across the gap and overlap with fingers from the other side. Cars drive over the interlocked teeth without feeling a break, but the bridge can still slide back and forth. Finger joints are elegant, but they have one big weakness: water. Rain and road salt pour through the gaps between the fingers, straight onto the structural steel below. Over years, that corrosion eats away at the heart of the bridge. Finger joints need drainage systems, collection troughs, and constant maintenance to keep the structure from rotting beneath them. For the longest bridges, even finger joints aren't enough. When a bridge deck needs to move more than about 20 centimeters, engineers turn to modular expansion joints. These are multiple small gaps arranged in a row. Steel beams separated by rubber seals, creating a sequence of mini gaps that add up to the total movement needed. A modular joint might have 4, 6, or even 8 individual gaps, depending on how far the bridge needs to move. Each gap only opens a few centimeters, but together they handle massive thermal expansion. That's the thump-thump-thump you feel on a long bridge. Each thump is one of those individual gaps passing under your tires. Inside a modular joint, there's more going on than you'd think. The steel beams don't just float. They're supported by bearing systems that let them slide, typically Teflon sliding against stainless steel plates. The friction is nearly zero, so the bridge moves freely without dragging against its own support structure. And it's not just back and forth movement. Bridges twist. They bend. A heavy truck in one lane causes the deck to tilt. Wind pushes the structure sideways. Earthquakes can move the foundations in any direction. The joints have to handle all of it. not just back and forth, but up and down, and rotationally too. The Tacoma Narrows Bridge collapse in 1940 is the famous example of what happens when a bridge's movement isn't properly managed. That was a dynamic problem, wind-induced oscillation, not a thermal one. But it drove home the point that bridges are not static objects. They're constantly in motion, and every component has to account for that. Which brings us to seismic joints. In earthquake zones, bridges face a completely different scale of movement. A magnitude 7 earthquake can shift a bridge's supports by several centimeters in seconds. The expansion joints have to absorb not just the slow thermal creep over months, but violent multidirectional displacement in moments. Seismic joints often use what engineers call fuse elements, components designed to break first, sacrificially, absorbing energy and protecting the main structure. When an earthquake hits, the fuse fails. The joint is destroyed, but the bridge stays standing. After the quake, you replace the joint, a relatively cheap, fast repair, instead of rebuilding the entire span. This is the hidden philosophy of bridge engineering. The structure isn't designed to be indestructible. It's designed to fail in predictable, manageable ways. The joints are the sacrificial layer. They take the abuse, so the bridge doesn't have to. And the abuse is constant. A major bridge might see over 100,000 vehicles per day. Each axle crossing a joint is an impact load. Over a single year, that's tens of millions of load cycles on a piece of rubber and steel sitting in a gap in the road. This is why expansion joints are the most frequently replaced component on any bridge. The deck might last 50 years, the main cables might last a century. But the joints, they're lucky to make it 15. On some bridges, joint replacement happens every 5 to 7 years. A constant cycle of cutting out the old, pouring new concrete, and installing new seals. When a joint fails and doesn't get replaced fast, the consequences cascade. Water gets in, steel corrodes, concrete spalls, chunks break off as the rusting steel expands inside it. What started as a failed joint, a relatively cheap component, becomes a multi-million-dollar structural repair within a few years. In 2018, the Morandi Bridge in Genoa, Italy, collapsed during a storm, killing 43 people. The investigation found years of corrosion and degradation in the structure's concrete-encased stays. Water intrusion contributed to that corrosion. The joints and seals were part of the story. Not the sole cause, but part of the chain that let water reach steel that should have been protected. Modern engineers are trying new things. Some bridges now use asphalt plug joints, a flexible polymer-modified asphalt that fills the gap and can stretch and compress without separate mechanical parts. Others are testing shape memory alloys that absorb movement and return to their original form, which could eliminate rubber seals entirely. But the fundamental principle hasn't changed in over a century. You can't build a rigid bridge. The materials won't allow it. The physics won't allow it. You have to build a bridge that moves, and then manage that movement with components that are small, replaceable, and cheap compared to the structure they protect. So next time you're driving across a bridge and you feel that thump-thump-thump, don't think of it as a rough road. Think of it as the sound of a structure breathing. Each gap is a calculated weakness. Each joint is a sacrifice. The bridge is coming apart, piece by design. And that's exactly why it's still standing. The most important parts of a bridge are the parts that look like mistakes. The gaps, the cracks, the seams, they're not flaws. They're the reason the design works. They're the difference between a bridge that lasts 100 years and one that destroys itself before its first winter. Every bridge you've ever crossed, every highway overpass, every footbridge in a park, they all share the same secret. They're built to move, built to flex, built to fail in the right places so they never fail in the wrong ones. The gaps are the genius, and now you know what they're for. Follow for more hidden engineering that's right beneath your wheels.